right, so we're going to continue our conversation about Riemann sums that we started in the last video. So essentially the Riemann sum, what we discussed last time, is that you don't have to have equal widths. So let's continue that conversation and look at how that might change things a little bit when we look at finding the exact area by letting the limit of the number of rectangles go to infinity, like we did in the last section. Last section, though, we had equal widths. So what happens with that idea if we don't have equal widths? So suppose we have this really basic function here. It's just the line y equals x. We're on the interval from 0 to 1. And suppose we take this partition right here, and instead of equal widths, this is the partition. And so I've already written in kind of lightly off to the side where a half, a fourth, and an eighth would fall on this interval from 0 to 1. And so now suppose that let's give this some endpoints here and actually draw in some area. So suppose we were to use left endpoints. So we'll kind of fill in this left Riemann sum for this particular partition here. Okay, so this is certainly valid as a Riemann sum using 4 rectangles, although the first one has a height of 0. So this would certainly be a Riemann sum with 4 subintervals. It's in particular a left Riemann sum. All right, but what if I continued this pattern and extended this idea from the last section of just letting n go to infinity? So what's the pattern I'm talking about? Well, you probably already saw that we went from 1 to a half, and then the next one was half of that, so at a fourth, and then an eighth, and the next one 1/16th, and so each time we're taking half of the one before that, or the one, I guess, to the right of that. But suppose we were to, take that pattern and just let the number of rectangles that I'm forming according to this pattern, letting that go to infinity. So again, if we were to kind of look at this idea, so we would start with our left endpoint here. And so let's just sort of draw this again in real quickly here. And so I'm just using left endpoints for this example. But now suppose we continued it and we were going to continue to put in then, I guess, what would be 1/16th, right? So then let's say we went sort of halfway in between here. I don't know, so if I can, squeeze something in here, maybe right about here. And then maybe we did half of that one, so it would be in here, and I'm very quickly not able to really draw anything more. So here I was trying to draw in like 1/16th in here. So I was attempting to draw in, this was supposed to be at 1/16th, and so on. I was trying to draw in, but it's very, very small, so pretty difficult to do. But notice that as I let this pattern of n, if I let these rectangles of unequal width go to infinity, more rectangles down here is not going to help. So, if I look at what's happening, in this region here, so looking at more rectangles in here, letting this pattern of n go to infinity, this is not closing in on the actual area. So I am not approaching my actual area under the curve because it's not doing anything about the primary error that we saw in the very beginning, where we have all this kind of white space. I used left endpoints, but it's not doing anything about all of this initial error. So rather than letting the number of rectangles go to infinity, instead what we need to do with this more general definition would have really been to, if we were kind of talking about this in class, I'd say, so if fixing this end of things didn't help, like where did I need to address? So I really needed to address the error kind of in the beginning here. So this is the error up here that we really need to address. And what we're doing in the lower left-hand corner, that's not helping. So what would help then would have been to have made these rectangles smaller. So here's where this definition is. We're going to say, okay, well, rather than letting the width or rather than letting the number of rectangles go to infinity, what we really need to do then is we need to let the width of the largest rectangle, or your book subinterval, we need that to get smaller and smaller and smaller. So we need that to go to 0. So the width of the largest rectangle, or the width of the largest subinterval, that's what we need to go to 0. And so incidentally, that would have worked fine even back with equal widths. To let the width go to 0 when you do equal widths is the same as letting the number go to infinity. With equal widths, as the number goes to infinity, your widths are going to 0. But here we really need to state it that way. So at the end of the day, this whole conversation is really just to help you to see why when we get to the formal definition of the limit of a Riemann sum, it's no longer the limit as n goes to infinity. Instead, it's this limit of letting the width of the largest subinterval go to 0. And that's the notation that you're going to see. So as we kind of think about this, if given a choice, we will default back to equal widths. But the more general definition of what we're now going to be defining as something called the definite integral is going to be letting, in the most general way, the width of the largest subinterval go to 0. So when this limit exists, we say that the function that is integrable, we're able to find this actual area then. So again, a lot like what we did last time, the only difference now being we're letting the width of the largest partition go to 0, or largest subinterval, and now we're no longer assuming equal widths, right? Because there's the delta x sub I. All right, so the notation that we are going to want to know then, and we're going to kind of go back and forth with a couple of examples, this is now defined to equal what looks like this. Think of this elongated S over here on the left-hand side. So I want you to think of this elongated S as the well, it's going to be the notation for an integral. But for right now, it's really useful just to think of it as S for sum. So think of it as the sum, a big elongated S, from A to B, so the leftmost point to the rightmost point of whatever your function is. And for right now, just kind of think of the dx as representing, remember when we talked about differentials, dx and delta x represented that change in x. So right now you can think of that dx as being this change in x, the width of x, and the f of x, well, that's the f of, like in this case, the u sub I. So it's this elongated sum from A to B of the f of x's times the dx, and then the notation is now equal to this definition of the limit of the Riemann sums. All right, another just little quick definition before we look at some examples here is that the norm is the width of the largest rectangle or largest subinterval. So the width of the largest subinterval is called the norm. And in your book, it's denoted by just max, so largest, and then width of a, delta x sub I. All right, so for these, all we're going to do right now is just go back and forth between the notation. So right now, if you saw, oops, here we go. All right, so if I say the limit of the max of delta x sub I, so the width of the largest subinterval going to 0, of the sum as I goes from 1 to n of 2 u sub I cubed times delta x sub I on the closed interval from -1 to 0. So we want to write that as the corresponding definite integral. So that's that elongated S notation. So right now we're just kind of making a connection between these two notations. And then much later we'll build on this. But for right now, just recognizing that these two are going to mean the same thing to us. So here's now we're writing it according to the definite integral is what we have on the left-hand side there. So this is equal to the definite integral from a to b, so -1 to 0. So thinking of that as that sum, I'm summing from -1 to 0. The f of x, well, this is the f of u sub I. So with that, I can see the structure. Oh, if that's f of u sub I, then this is really 2, the u sub I, that's the x cubed, and then dx. So now when I want us to think about finding the Riemann sum, I could just write it this way. From -1 to 0 of 2x cubed, the definite integral from -1 to 0 of 2x cubed dx, that means this limit of the Riemann sum. All right, so let's look at another one here. Oops, did not mean to hit that. Where was I at here? Okay, next one. All right, so that was first one. Now let's look at one where we're actually going to approximate what the definite integral is using the specific Riemann sum that we specify here. So let's look at another example. And so this one we're going to have the definite integral from -3 to 3 of 2 to the x dx. And I want us to estimate or approximate that definite integral using 4 subintervals of equal width. Oh, and I need to specify, oops, sorry. So using 4 subintervals of equal width, and we'll use right endpoints. So with right endpoints. Okay, so this is how these examples are, how you're going to see some of the problems you'll have to do in your homework. All right, so first of all, notice that I am back to an approximating situation. So anytime we're being asked to approximate the definite integral, then that means we're going to have to be using like a finite number of rectangles, and we have to be told, what kind of endpoints that we're being asked to use. So we're back to an approximate situation, and again with an equal width in this case. So this is really what we did in the previous section. So the first thing we're going to find is our width. Oops, gosh darn it. And our width in this case, or since we're doing equal widths, is going to be our delta x with equal widths is the b minus a over n. So b in this case is that upper limit of integration, that 3, minus the a is that -3, and then all over, in this case, my n is 4. So we end up with 6/4 or 3/2 or 1 1/2. So remember, this is our common width that is going to be out in front here, and then times the f of, and now using right endpoints. So the function f of x is the 2 to the x. So 2 to the, all right, so right endpoints, remember, you're going to start in one width. So maybe it helps, even if we don't draw the full picture. Gosh, I keep hitting that today with my hand, sorry. So sometimes even if we don't draw the full picture, although certainly we could here, maybe I will do that. At least thinking about what happens on the x-axis might be helpful, the breaking of this up, the partitioning. All right, so this is, oh my gosh, I keep doing that. Must be how I'm holding it today. All right, so here we are, here's our function 2 to the x. And so we are looking at this on the interval from, not necessarily drawn to scale, but let's say right about here, from -3 to 3. And so we've just realized it's going to be widths of 1.5. So this would be at -1.5 or -3/2, and then at 0, and then at +1.5 or 3/2. So there's how this partition would look. And now using right endpoints. So on each of these, we're using the right endpoints. And so this is roughly what my graph here would look like. Okay, so we've used, sorry, this one's kind of sloppy here, but we've used the right endpoints on that. Okay, and so here was my function in there. All right, so a sketch sometimes helps. You certainly don't have to do it. At minimum, you want to just think about, okay, when I do the first height, it's going to be one width in. So it's going to be 2 to the -3/2 or -1.5. And then plus f of going in again, another 1.5 would put me at 0. And then the third one, 2 to the 1.5 or 3/2. And then the last one would be our 2 to the third. So with right endpoints, that's what we would have here. And so subbing this into our calculator, this would come out to be, I did this in advance, so this one, oh my gosh, I do that one more time today. So this is going to come out to be approximately 18.27. So this would be our approximation for this definite integral. So that would be our approximation. All right, so we have a couple of basic properties of definite integrals that you could maybe think about reasonably. If maybe you just think about like the equal width case like we just did here, and we think about delta x, for example. So think about when we just did delta x up above. If your a and your b are equal and they're both a, when you would find your delta x in that process, your delta x would have been a minus a over n, and so this would have been 0. So when you think about what would have happened here, if we would have had a common width of 0, so this would have been 0 then times, some sort of a sum, that of course is going to come out to be 0. And then over here, if I think about what happens, so notice I've written this in a less traditional order, right? This is the definite integral from b to a. So if you think about what happens here with your delta x would have been the a in this case minus the b over n, just because of the location here. That the a is now in the upper limit location and the b is in the lower. So it's the upper minus the lower divided by n. Okay, well, think about what happens if I wrote this in the more traditional order of integral from a to b. That's how you've seen it. Well, in this situation, our delta x would have been upper limit b minus lower limit a over n. Okay, now everything else about this would have been the same. So the sum would have been the same sum. So then you're multiplying by some sort of a sum. So these two are almost equal to each other, except one of them has the order of a minus b and the other has b minus a. Well, guess what? In either of those, if you were to factor out a negative, that can change your order of subtraction. It's kind of how we say it. So if you think about that, that's minus a and a plus b. Yeah, that's the same as b minus a. So now if I factor out that negative, I now have a minus b over n, and that's times the sum. This is the original one. So what does this really mean? It means that if you change your limits of integration, you're going to get the opposite result. So I'm going to erase this work just because it looks so sloppy. And so here's what we end up with here. So if your limits of integration are equal, you're going to have 0. And if you change your limits of integration, you're going to get the opposite result. And then one last little theorem here. If a function is continuous, then we are able to find this definite integral. So, just kind of think about, let's take a peek at this graph up here. So we were certainly continuous from -3 to 3. So on this closed interval from -3, looking at this graph, yeah, we're definitely continuous from -3 to 3. So as long as we're continuous, we're going to be able to break this up into, some sort of a partition, and eventually, if we want to, we can let n go to infinity or let the width of the largest partition go to 0. So as long as we're continuous on that closed interval, we will be able to find this definite integral. All right, so let's take a look at kind of a short example here. It says evaluate using the limit definition. Now again, our limit definition, I don't know why this is a screen capture from the book, but is going to be the integral from a to b of f of x. So this is the most general form where it doesn't assume equal widths. So this is, I guess I'll say, the general Riemann sum definition. But if given an option, we're naturally going to default to the case where we're going to assume equal widths. So this is the equivalent form if we're assuming equal widths. Well, we're going to assume equal widths, right? So why wouldn't we? So if given any sort of a choice in the matter, we are going to assume equal widths. So essentially, we're going back to, again, what we did in the last section. So a lot of this section is putting new notations and definitions on things, but in a lot of cases, we're reverting back to most of the things that we developed in the last section. All right, so that's what we're going to do then, is we're going to assume equal widths. Okay, so if I assume equal widths, I'll put my little asterisks here, we're going to be looking at the limit as n goes to infinity of the sum as I goes from 1 to n. Now, the f of function here, we don't really even have any place to put in a u sub I or a c sub I or anything like that. This function's just plain old 5. So that's just going to be 5. And then times our delta x. Well, our delta x with common widths is going to be the b minus the a, so upper minus lower, divided by n. All right, so that is the delta x. And so what we have, this is probably the shortest one we've ever done with these, is simply going to be, this is going to be our 3 over n. Well, 3 over n can be brought in front of the sum because it doesn't have the index I in it. It's just a constant multiple. This is kind of how I did these in the last section. And then the sum as I goes from 1 to n of just 5. We had a formula for that in the last section of a constant is that constant times n. So we have the limit as n goes to infinity of 3 over n times n. And so, of course, we can, n over n becomes a factor of 1. And then as n goes to infinity, if we have a constant, that's just going to equal that constant. So 15. And so that's what we end up with here. Now that kind of makes sense. Doesn't kind of make sense. It definitely makes sense if we think about this really simple graph here. We were going from -1 to 2. The function is just 5. So this is just f of x equals 5. And so when we think about what we get here, it's really just in a graph, it's just a rectangle. So if we think about this as this area here, oops. So if we have this area, I just wanted to shade this area right here. So if we just think about this area right here, then that is simply going to be, oops, sorry, I'm still getting used to all my little tools here. Let me just redraw this. So it's an area of a rectangle, so it doesn't really get much nicer than that. So we're really just looking at the area of this rectangle. And so the area of that rectangle is quite simply going to be the 2 minus -1. So that ends up giving us the width. The 2 minus -1 is the width of this rectangle, and then times the height of the rectangle, which was 5. And of course that's where we ended up with the 15. So this leads us to this little observation. So if we are just integrating a constant, so in this case the h is like the 5 in the last example, so it's going to be that 5, that h, and then times the width, so the b minus a. So, oops, I started to write the 2 there. So this is the b minus a. So b minus a. So just a little observation that we can make there. All right, so we'll stop here for this video, and then next time we will come back and we will take a look at doing just another couple of using this definition, kind of getting back to really what we ended the last section with. So a lot of what we did here today in terms of the actual work involved things that we did in the last section. So I suppose the most important part is just recognizing this new notation that we're working with here, which is the general form for the limit of a Riemann sum where we don't assume equal widths, and that's why we have this letting the width of the largest partition go to 0. But whenever we're given a choice, if we're going to work a problem, we're going to assume the equal widths case. We have the general and then the equal widths. We're going to kind of just by choice resort back to equal widths.